Yeah. Good afternoon, everyone. First, I would like to thank the organizers for the possibility to give a talk here. What I want to talk about, at least partially, it's a joint work with Dirk Hundersmark and Marcus Lange. So just the outline. First, I would like to just introduce what I mean by somehow this quantum states at the brink and what are eigenstates at the threshold of the essential spectrum. Then I would set a problem what I'm tackling, and then somehow there will be the results about the existence and absence of threshold states, and also some results about when actually or what kind of finite moment these states have. And at the end, I have some examples. So first off, somehow the bound states in quantum mechanics, they are important. They somehow relate to the stability of the system. So the systems which I'm looking at is essentially a Schrödinger operator. So we have kinetic energy plus a potential here. The potential is just separated for the positive and repulsive part. And then for such an operator, the typical spectrum will look like that one has the essential spectrum going from 0 to infinity or going from some finite number, and then there will be some discrete eigenvalues. And now the question is, what happens when this discrete eigenvalue, if we change the potential, then the discrete eigenvalues will change. And then the question is, what happens when they somehow touch the essential spectrum? Because in principle, they can either survive this touching or they can disappear. If they disappear, they somehow can become resonances. If they survive, they really are in a point spectrum, but not in a discrete spectrum anymore. And what is actually known is that their destiny is decided by actually the asymptotics of the potential. So what was known already in the 30s, people found out that if you have a long range repulsion in our system, specifically they were interested in a Coulombic repulsion for the actual nuclear decay of nucleus. They found out that actually the long range repulsion can stabilize your system. This was further studied on by Hoffman Ostenhoff and Simon in the 80s, where they were really interested in what is happening for the hydrogen anions. So one infinite heavy nucleus, 2 electrons. And what they were doing is that they were tuning the repulsion between the electrons until there is only one bound state left, and this bound state touches the essential spectrum. And they showed that for the Coulombic, for this specific system, this state survives. Or better to say, it survives if it's in the singlet form. If it would be in the triplet form, it disappears. This was generalized for general systems where you have a Coulombic repulsion. That was by Bose and Schweiger in 85. Furthermore, the people showed later on, Ben-Gurion Yaour, then if your potential decays fast enough around infinity by decaying fast in 3 dimensions is 3/4 1 over x squared, and also there is the logarithmic correction, then there is no chance for your system to have 0 energy eigenstate, because intuitively you can think about it that if your particle wants to leave the system, then it would need to tunnel through the repulsion. And if there is not enough repulsion, then it can somehow tunnel to the infinity. And actually this is applies to the asymptotics, which prohibits the particle to tunnel through. The opposite, the existence result, was then showed by Gridneff and Garcia in 2007, where they showed in dimension 3 again that if you have potential which decays slower than this 3/4 x to the square, then you will have these threshold states, and they somehow may replicated also the result by Ben-Gurion and Yaour. So now what's the setup? So essentially I have a self-adjoint realization of this differential form. This is just standard Laplacian plus potential. The potential needs to be somehow in a reasonable class, whereas the reasonable class is just somehow taking the local Kato class. So you don't need to worry about too much about the self-adjointness of such an operator, because everything then comes from the self-adjointness of the Laplacian, and then everything else follows to standard results. And we will look at the weak solutions of this differential equation. So this is really corresponding to U being kind of eigenstate of corresponding to the eigenvalue 0. So, and now the goal in this setting is to find sufficient necessary conditions on the potential to have bound state at the threshold, so to have L2 solution of this equation, actually to not have such an solutions. And also then another question is when such expression here is finite for such a threshold state. So this means that especially this could be interesting for C equal to 1, because that was actually when I was discussing with one physicist that for them, or for him, it was essentially state was localized if the mean value of its position was finite. So, and that's also the question somehow whether if your psi is L2, but if you try to localize the electron, you cannot find it in a finite region. It's a question whether it's truly localized or not. So that's the setting. So now, just maybe for the purposes of the theorem, I will also need, for the terminology purposes, what's critical potential. The critical potential is a potential if you have an operator, then we say that its potential is critical provided that adding arbitrary compact operator in this sense would provide a negative eigenvalue. So if you think of H, your origin operator, which has a spectrum 0 infinity, which is only essential spectrum, then you say that the operator is critical if adding arbitrary compact perturbation of this operator would generate you some discrete eigenvalues below the threshold. So very often one can find in the literature that if the Schrödinger operator is with a critical potential, then very often it says that 0 is energy resonance or that this operator has a virtual level. And by this virtual level, it's really that there is either L2 solution of the equation from the previous slide, or there is somehow something which is not L2, but it's something which doesn't diverge crazily around infinity. So some examples of critical potentials. So for dimension 1 and 2, it's trivial potential, so V equal to 0. So for the, also you can find some non-trivial potentials, but then actually this potential will need to change the sign, and overall integral of such an potential needs to be strictly bigger than 0, provided that this is not infinite. And for the higher dimensions, you can always just simply look at the Hardy potential, and then that's a nice critical potential for arbitrary d bigger or equal than 3. So now we can turn our attention to the absence result. So the absence result says that if you have operator which is positive, then it cannot have eigenvalue 0, provided that the potential decays faster than this expression right here asymptotically. So what's really interesting here is that there is a term which depends on the dimension. So there's actually something interesting happening in dimension 4, and then for higher dimensions, actually this term becomes negative. So that's actually also the reasoning why there are usually no 0 energy resonances for compact potentials for dimension 5 and bigger. And for dimension 4, you actually need to take the first correction term in form of these logarithms. Here, what's happening is that you just take this ln k is just taking logarithm k times. So the first correction is just 1 over x squared, 1 over logarithm of x. Then the second correction would be 1 over x squared, 1 over logarithm x times 1 logarithm of x. So this is the absence result. For the existence result, it's quite similar. So here, just the addition is that the potential will now needs to be critical to actually make sense of this question. And then we say that we can say that the 0 is eigenvalue of this operator, provided that the potential is bigger than this expression right here. So these first two terms, they are the same as for the absence result. And now we just enlarge the largest of the smallest correction by epsilon. So we add just this last term from this expansion, and then suddenly there will be a point eigenvalue at the threshold of the essential spectrum. So just to somehow show this somehow in a more compact form, there is like the first three terms in the expansion. So here for the absence and for the existence, you just add epsilon to the smallest of the corrections, and then you can either have a bound state at threshold or actually it's not present there. So now one can also similarly look at the moment, and now the condition will be quite similar as for the existence result, but it will say that if you want your eigenstate at a threshold to have a finite x to the c moment, you actually need the, for this to be unbounded, you cannot have a potential which decays slow in a sense. And by slow, what one means is this expression right here. Here, just for the sake of not writing complicated formulas, I just wrote first three terms. But here one can see that to the first term, you need to add c squared plus 4c, and that to each consequent term, one needs to add this c half. So, yeah, so this is precisely the formula. So in a sense, one can think of that if your potential decay is fast enough, then you will not have neither resonance nor eigenstate. Then if your potential becomes somehow repulsive enough around infinity, then you will start having an eigenstate which has practically all moments infinite. And then somehow when you move further on, whether even your repulsion starts to be bigger and bigger, then more and more moments will become finite, up to the case when actually all the moments, so all the polynomials or the expected values of the polynomials of x will become finite. So this also means that somehow really the critical potential or the special potential is 1 over x squared, which is not that surprising because 1 over x squared is just potential corresponding or somehow scaling of the Laplacian. That's not that surprising. So for the finiteness of these moments, it looks practically the same. One just needs to add some epsilon correction to the last term. Here, just a small unfortunate thing is that the factor which is with the highest term is also with this 2c, which is somehow slightly worse than in previous case when you could just take epsilon, which was kind of independent. And here kind of for bigger c, you somehow need to tend to take a bigger correction in a sense. Even though you can take epsilon arbitrary small, you kind of cannot take it uniform in a sense. So that's the condition for the finiteness of these moments. And now maybe just some examples. So as I mentioned with the critical potentials, what's kind of important with the critical potentials generally is that somehow every, if you have a zero energy eigenstate, then your potential needs to be critical, but the converse does not hold, because you can have a critical potential which only has a resonances. Such an example is, for example, already potential which we thought, so potential corresponding to the Hardy inequality, because Hardy inequality is optimal in a way that you cannot kind of enlarge this potential and still be positive operator, but at the same time, Hardy inequality doesn't have L2 minimizer. So that means that there is kind of the optimizer, which is not L2, which would correspond to the So now just somehow one example of a potential which would in a sense be critical and would go through all the various behaviors, one can say. So we have this kind of potential that depends on alpha, and this is just a dimension. So if we would take minus Laplace plus this potential, what one can say about this operator is that it has a purely essential spectrum from 0 to infinity. If you take alpha bigger equal than 0, then the operator is in fact critical, and it will have a virtual level. And then actually here will be transition for alpha big enough in a sense that if alpha is small equal than or between 0 and 1, then 0 is not an eigenvalue, and suddenly when alpha is bigger than 0, bigger than 1, then 0 will be a proper eigenvalue with a L2 eigenfunction. And actually, we have also explicit formula for how the ground state or this eigenstate or resonance looks like. So it's just this thing with a polynomial decay. And if alpha would be less than 0, then this potential is actually subcritical, and 0 is not an eigenvalue of resonance. For us, we considered zero energy resonance to be that it needs to be weak solution of a Schrödinger equation, and that it cannot somehow grow exponentially around at infinity. There are different definitions how one defines. Yeah. Yeah. For us, casually speaking, somehow it's not L2, but it cannot diverge too far in a way. So the derivative is H1 still. So for us, it was H1. Or somehow considering it as a big solution. So here one can just see how these potentials look like. So what one will see here is this is for the dimension 1. The blue curve will correspond to this potential V alpha or V gamma D from the previous slide. And then in the red, there will be how the ground state looks like. And also somehow when it will start to exist, here will be C, which would correspond to what kind of moments will be finite for this setting. So let's see whether the text will work or not. Yeah. So here one can see that this is still the subcritical thing. Now, what will happen is that there will be some potential well and two walls, which will prohibit actually electrons from tunneling away. And now it's just how it would look like. So, and it goes really slowly. So how usually it goes. But one can somehow see that if we start to have a deeper potential well, then actually we need to have a lot of repulsion to somehow combat the energy requirement for the system to be really positive. So here kind of the well goes really deep, and then the walls need to be really, really long. And yeah. So that's one example of such a state at the threshold. So now, just to summarize, so what I have shown to you is how kind of the asymptotic expansion for the potentials which either have or doesn't have bound state at the threshold of the spectrum can look like. Here are just somehow these low, these expansions for the low order, so just for the up to 2. And here somehow for the existence, just take C to be equal to 0. And for the moment, there is also these terms depending on a C. And the potential result that was already published and it's in this paper. So if you have any questions and I'm able to answer it, then I will do so. And thank you for your attention. Yep. Yeah, this was just somehow general think what happens, because what we are interested in, if you vary your potential, then what happens when it somehow touches the potential spectrum. Somehow, what one could say is that existence result would also be valid for also these 2 points. But all, yeah. No, what we have used is that we used actually subharmonic comparison principles. So what we did is we just created estimates on the eigenfunction from above and from below. So for the existence result, we have somehow calculated how we took a function which is L2, and then we asked what would the potential which would have this function as an eigenfunction would look like. And then this gives us the upper bound how the potential needs to look like for the eigenstate to exist. And then on the other side, we took a function which is not L2 and had it, and this gave us the lower bound on the potential in a way. So that's the how one can do that. This one's what? Okay, so the Marcel Majocha. Hello. That's right. Hello, everyone. Thank you for being here. My name is Marcel Majocha. I'm the student from the Faculty of Physics, University of Warsaw. Yeah, I'll be a master's student in next month, and I'll talk about my bachelor thesis, which I done under the supervisor of Marcin Napierkowski, which is about the ground state energy of a dense postgas. Okay, I'll start by formulating the problem. So let's say that we have n particles interacting Bose-gas in the box of the with the size of length L with periodic boundary conditions. Yeah, so the Hamiltonian of our problem will be given by minus Laplacian plus pairwise interacting potential. Yeah, the wave functions of this space are just we just take the L2 space, but the tensor product of it, the symmetric tensor product, and n times. And as for the potential, yes, Spirax is symmetric. It is positive, and its Fourier transform is also positive, and they are both integrable on the whole space, R3 space. I'll define the ground state energy in the thermodynamic limit, which is just the ground state energy, defined by divided by the volume of the box, and we take the thermodynamic limit. And I mean, just take n L to infinity, conserving the density. And the theorem that I was proving during my thesis on my thesis is just we have the following asymptotics for the big rho. And before I start talking about the sketch of the proof, I want to talk a little bit about the history of the problem. So it was first derived by Lieb. He actually proved the lower bound, and he sketched the upper one for this problem. It is worth mentioning that dilute gas is much more popular, and there are many results over the last decade. And I want to say about the proof of the Lieb formula in 2020 by Fermi and Soloway. But also there was a lecture yesterday also about one of the problems connected to dilute Bose-gas. And as for the dense Bose-gas, you can do a proof. It is quite straightforward in the grand canonical ensemble. So for reference, you can read about it in the work of Mokshansky and Pouba. What I mean is just working on the entire Fock space, and the results on the canonical ensemble. So the results on which in the ensemble that I was working with, you can achieve it
using the equivalence of ensembles, which works in this case. And the goal of my project was to derive this result working directly in the canonical ensemble. So just to prove that the energy for the fixed number of particles, the ground state energy has the following asymptotics, because it is much more interesting. Okay. So to prove it, we'll just we'll just show the lower bound for the overall and the upper bound. The lower bound is like very easy because we just have to use Pythagorean inequality, which is quite easy to prove. And also, yeah, and this is just the lower bound for our potential. And additionally, using the fact that minus rotation is positive, we have the following operator inequality, which leads to the lower bound. As for the upper bound, yeah, maybe I'll just mention that it isn't like always the case. I mean, in many cases, the lower bound is much harder than the upper. But because for the upper bound, you can always use the variational method. So by E0 of n of rho, I just denote the ground state energy of the particle Hamiltonian. So yeah, it is of course smaller or equal than the energy of any state, assuming that it doesn't have to be normalized, so I just divide it by the norm squared. And by taking so we are looking for the state for which we'll find the upper bound for which the upper bound will be small enough so that we'll be able to prove our theorem. And our state is inspired by the Bogoliubov theory. So just briefly speaking, the theory in which we assume that our Hamiltonian depends like the quadratic Hamiltonian for which we can define the ground state. And I'll just briefly tell you about what are those terms in our state that we defined here. So first of all, maybe we have this UN operator. It is the operator that works from our nth particle here, but it's the truncated excited Fock space. And what I mean by that, the excited Fock space will be the Fock space of the orthogonal space to the span of U0, where U0 is just the zero momentum plane wave. And by truncating it, I mean just when you look at it as the direct sum, you just take the n+1 first spaces because the first one is the zero particle one. So we'll just have max n particles you can say. It was also introduced quite recently, and it is used to implement the Bogoliubov number substitution canonically. The second term that appears in here is just the Bogoliubov transformation. So one used for diagonalizing Bogoliubov Hamiltonians, which is given by the following formula. AP star are of course annihilation creation operators by the fifth momentum plane wave of the fifth momentum plane wave, and beta of p is some real positive continuous function which we are choosing as like which we were choosing later. So we are first estimating it, and we were looking for such a function for which we'll find it with lower bound, upper bound, and U beta works on the excited Fock space from the excited Fock space into itself, and because here we have the truncating term, we also have to introduce the this one operator, which is just projection from the excited Fock space vector to n particles. And last of all, omega is just the vacuum state of zero particle normalized state. So for this psi n, Yeah, we'll also, because we introduced this one here, it isn't a normalized state, and therefore we also had to, like, during estimations include that we have the inverse of norm here. So for this state, we were estimating this value, and yeah, after like going through like thermodynamic limit, we got something that was dependent on this beta, and we chose beta so that we're able to find the right result. So that was the proof. That's the sketch of the proof of the upper bound. And for the last section, I just wanted to talk about the most interesting problem that appeared during our estimations. And it is connected to estimating this term, because when we are calculating this transformation, so UN, HN, UN star, it will give the following formula, and the thing that appears here is n plus is just the number operator on the excited box space. Here are those square roots. So we don't like the square roots because it's hard to calculate anything on them. So that's why we were estimating it from above by the powers of n plus. And when we found some estimation for the square root of this operator, we then use the Cauchy parts to like estimate the entire operator. And it usually works for this square root, but here in our case, so in the thermodynamic limit, we had some problems because when we tried to estimate this term, so when we tried to estimate this term in this usual way, it always gave us an upper bound that was diverging in a thermodynamic limit, and always it was the same rate. So no matter how well we tried to estimate like the square root, it always gave us something that was as the 1/2. And to deal with this problem, we introduced the V operator. This is the parity operator in the Fock space. So we use the fact that this state has a certain symmetry, and this term isn't conserving this symmetry. And the symmetry I'm talking about is just the even number of creation and annihilation operators. So what I mean by that is when we this operator is conserving the symmetry of even number of creation and annihilation operators. I mean that when we take the product of creation and annihilation operators, and it's the even number of terms in there, and we transform it by this term, it gives us this product. When there is an even number of it, it gives us minus. And because U beta is conserving the symmetry, it is how it turns out. It is the spectral projection of n plus, which also conserves the symmetry. And yeah, it is the vacuum state. We can like this formula holds, and because here we have the function of n plus, and here we have like the cubic terms. So there are like creation and annihilation operators, which we have the minus here. So when we try to calculate this term, it gives us that it should be equal to minus this term. So it has to be equal to 0. So that's how we dealt with it. And yeah, that will be all from me today. Thank you for your attention, and I want to thank Marcin Majocha and Bose Ruba for helpful insights and discussion. Yeah. So the point is that when you have this definition, so for the grand canonical one, you'll just have like the state on the entire Fock space. For that, we'll have that the number operator on it will have at least will be equal to at least n. And we know that this for sure holds from so this for sure holds like from one side, that one is less or equal than the other. To show that we will get something that something like in the other way, I think that you can look for the proof in Rawls' book, for example. Yeah, but so it maybe it isn't like very trivial, because I know that there is like for sure there is like the proof with the equivalence, like with the equality here when we are dealing with the potential that is compactly supported, and I'm not sure if it will for sure like give us the exact result when there is complexity. I didn't pass. Can you repeat? Because okay. Well, you can say that it somehow could help, yeah. When W, can you repeat? I'm sorry. Yeah. So we assume that our W is finite. Yeah, we are assuming that W is finite. Okay. Yeah, of course. It's a good thing to think about it, but I haven't think about it. So I don't know how is it like doing everything. Okay, go ahead.
Yours. No.
The third
Thank you very much for the introduction, and I would also like to thank the organizers for giving me a chance to speak. So I will be talking about the momentum distribution. I'll let you know what I mean by momentum distribution, then the high density case of Fermi gas in an approximation that is the random phase approximation. I'll also tell you what I mean by random phase approximation. Okay, so familiar setting again. I consider n spinless fermions in a torus that is of side length 2 pi. Then I consider a Hilbert space, which is just the L2 antisymmetric sector of the L2 P3n, and then we take an n-fold tensor product to build the Fock space Hn or F, I would later interchangeably use. And then any vector or the wave function that belongs to my space is such that it describes fermions. In a sense, it's antisymmetric, or under any transposition, it only incurs then the sign of the permutation. And to describe such n fermions, I consider the Hamiltonian, which is just the kinetic part, the Laplace operator, and then a potential. And in front of the potential, you see there is a lambda. That's the coupling parameter, which lets me scale the energies between the kinetic part and the potential part. And I work in the mean field scaling. So in the mean field scaling regime, and since I mentioned that I would be doing high density, the aim would be to take the particle number n to infinity. The interaction is weak, and the key point being the mean particle distance is much smaller than the interaction rate. So what it means is all the particles would experience interactions with all the other particles. And the aim is, the aim of being in the mean field scaling regime is to somehow balance the kinetic energy and the potential energy of the system. And to do that, we choose this lambda as lambda scales as n to the minus 1/3. This allows us to balance the kinetic and the potential energy of the system. And now to begin, in the case when we don't have any interaction potential, 0, we know exactly what the ground state is. It's just the n-fold antisymmetric tensor product of plane wave states. And we know how the energy is in that state, what we can do. And since the particles occupy plane wave states, they are fermions, they cannot occupy the zero momentum states, as in the case of bosons. They fill lattice points in the momentum space. And we call the complete filled state, or all the states, when they're filled, they occupy a sort of ball in the momentum space, and that's what we call the Fermi wall. And the Fermi wall is just defined as the momentas belonging to the lattice such that they're smaller than our Fermi moment. And the number of particles is just the size of the Fermi wall. Again, this kf scales as n to the 1/3. Okay, so in the case when v is not 0, what we can do? What we do is we use the Hartree-Fock approximation. The validity of Hartree-Fock approximation in studying fermionic systems has been well established. One can refer to the works of Secco, Bach, Graf Solovay. And there, what we see is Hartree-Fock approximations holds true for fermionic systems as well. And in that approximation, we can take a state which is similar to the n-fold tensor product of the plane wave states, but here these are not plane waves, and these are n orthogonal functions belonging to our space L2 of T3. And we take an antisymmetric tensor product as from the lecture yesterday, we see that it comes at a state of determinant. And one point, also this state minimizes our energy Hn or En. Okay, so now what do I mean by momentum distribution? Momentum distribution I defined by NQ, and that NQ is just the expectation value of A star Q AQ, where the A star and where these creation and annihilation operators live on the momentum space. And I just want to find this expectation value for different Qs or for all Qs. And again, we have this Fock space that we built, omega being the vacuum state. And what do we expect? So in the case when there's no potential, we expect a step function for the momentum distribution, as evident by the Fermi law. There is a ball that is filled up until the Fermi momentum, and then there are no more particles. outside the Fermi. But what is expected for the case when the interaction potential is not zero is that it deviates from the step function. So there are excitations above the Fermi surface which change this nice step function behavior or this occupation profile of fermions. And we wanted to find what it is. And now, since I talked about Hartree-Fock approximation, even in the Hartree-Fock approximation, what we see is the same behavior. It's a nice, well-defined step function, no particles outside Fermi ball. But as predicted in the physics literature, there are particles that go, or there exist fluctuations. So what about going beyond Hartree-Fock? And to go beyond Hartree-Fock, we prove this result, which is about to appear with Niels Benedicter and Sasha Lee. And so the result states that for any interaction potential such that the Fourier transform of the potential is in L1, it's positive, it's zero at zero, and it's symmetric. Then for such potentials, there exists a sequence of Kf. There is a slight abuse of notation here. It should not just be Kf, but Kf sub n. But just to ease the notation a little, we chose to just write it as Kf. So there is a sequence of Kf such that Kf tend to infinity, and the number of particles that we have is just the number of particles in the ball. Then in such a setting, there exists a sequence of trial states, psi n, again indexed by the number of particles, such that each psi n lives in the antisymmetric sector of the L2 defined or n torso. So with these things set, the trial state is such that it is energetically close to ground state, and in which sense? In the sense that the ground state energy, the difference between them is bounded by Kf to the 1 minus 1 over 6. So this sense of being energetically close is achieved by this concept of random phase approximation. And in random phase approximation, we get this, or in other words, in literature, it's always referred to as the bound on correlation energy. So we work with the same state where we can achieve such bound on the correlation energy, and in that particular trial state, we have our result. And that result is that there exists constant C1 and C2, depending on the L1 norm we have, such that for all Kf and all Qs, we have the momentum distribution defined by NQB. I'll tell you what NQB looks like. It's not very interesting to look at the formula itself, but the NQB is the bosonized excitation density, and it's bounded, or it's with order Kf to the minus 1 times EQ to the 1 minus 1. The EQ, the function that we say is just the excitation energy, or the energy above or below the Fermi surface. And then we bound the errors, or the errors is of order minus 7/4 in Kf, and again, the factor of EQ to minus 1. And now the interesting thing is that we could actually show that there exists such excitations above the Fermi surface and how they are, and also this particular thing has implications in the universality class of Fermi liquids. So we actually show that we do have a discontinuity in the momentum distribution. And now I'll give you a brief sketch of the proof. So the trial state that we take, psi n, is such that we can recover the energy up to such order. First is just the kinetic part, which scales as Kf to the 5. Usually it's written in terms of the number of particles, so it might look a bit weird, but it's the same scaling as one expects or one sees in particle number. Then this is the direct interaction part, the exchange interaction part, and then the contribution that comes from random case approximation. Now, how do we construct such a trial state? We define two transformations. One we call particle whole transformation. It's a unitary transformation that acts in such a way. Or if you want an intuitive way to think about it, it shifts perspective of the problem from the origin to the Fermi surface. So we do our calculations with respect to the Fermi surface, and that's what this transformation achieves. Then we define an almost bosonic Bogoliubov transformation. We know, we just heard what Bogoliubov transformations do. So we define the Bogoliubov transformation in such a way that this particular big operator is anti-unitary, and then when we exponentiate it, it's a unitary operator. And it's again quadratic. But it's a bit weird to call it quadratic because these are not the standard creation and annihilation. That's why we call it almost bosonic, because these are not fermionic creation and annihilation operators. And what these operators are quasi-bosonic creation and annihilation operators, and these are just a product of two creation, two annihilation operators to define the quasi-bosonic creation and annihilation operator. And they're defined on a set for Qs in Lk. And Lk are just a set of Qs such that Q belongs to the intersection of the complement of the Fermi ball and the shifted Fermi ball. So you see this set which looks like a loon or relating to the moon. We call it loons, but yeah, these operators are defined on such sets. And they follow approximate CCR relation. So we call them quasi-bosonic canonically commutation relation. And we see that we do get a delta, but we also incur an error term every time by doing this commutation relation. And this error is defined as this. And the problem for doing the analysis is to care for this error that does not let us consider the pair of fermions as bosons. So in this setting, we define what we try to calculate is this. You might notice that I didn't write any R operators here because they're fairly trivial. We can just choose our reference point at the Fermi surface and then get two cases for Q in the Fermi ball and Q outside the Fermi ball. And to calculate this, we start by doing an iterated UML expansion. We do UML again and again. And as we do UML of such a expectation value, we incur commutators. And those commutators, to treat those commutators efficiently, we introduce these two operators. And the standard or the technique that was used before in the paper by Benedict Teril was that it was expanded as a sequence of nested commutators. But what we do is we use these two operators and expand our commutators as a sequence or the expansion in terms of anti-commutators. So these operators are again quadratic in the quasi-bosonic creation and annihilation operators. I write they're defined for a symmetric family of symmetric operators, and I just write them as A because these A would change for every step of DML that we do. So after doing n steps of DML, we recover these three terms. Actually, there are 5 terms. 2 of those are just expectation values of our quadratic operators, which I defined before. And those, the expectation value of such quadratic operator goes to 0 because they're normal order. So at the end, we have these 3 terms. So the first one is our contribution, the one that we wanted. Then there are errors, and then there is the end of the DML. So after doing n DMLs, you end up with a thing, and that's what we call the tail term. And as I said, we expand the series in terms of nested anti-commutators. So that's how we define nested anti-commutators. And to distinguish between which quadratic operator ends gives us the contribution, we define sigma n, which is either 1 or 2, which just gives us Q1 or Q2. And then the error terms are defined in such a way where they are again E, Q, and the indices change depending on where we are in the expansion. And they also operate on the nested anti-commutator. And now we take the limit n to infinity. In a sense, we do infinite number of QMLs. And in that limit, we see that the leading order is this cost term, the errors, and that's all. The tail term, in the limit n to infinity goes to 0. So we're safe there, and what all that we have to worry about the errors, we recovered the leading order. And the thing that I mentioned, NQB, our correction is this not so nice thing to look at, but it agrees with the results in the physics literature. And it also gives us the scaling that I mentioned of kf to the -1 times EQ to the -1. And this formula is just achieved by using some simple integral identities and some simple functional analysis, and one can achieve this, where these lambdas and GLs are defined in such a way. The second term is just the error, and the last term goes to 0. Now, how we do the error estimation, that's another part, and it involves a nice technique. So we start with the error estimates. We look at each error term, or look at the term of order m, and then bound it for any n. And we do that in such a way that we recover enough powers of kf, or negative powers of kf, and something we call the bootstrap quantity. Bootstrap quantity is again just the supremum over what we try to find. And by having this constraint, we get the momentum distribution as some function, the one I defined before, the scaling. And this is the error bound, which is bounded in terms of the kf and the bootstrap quantity. But while doing the error estimations, the first task was to normal order all the errors. And when we normal ordered all the error terms, we see a peculiarity is that there were certain terms which did not involve any creation or annihilation outcomes. In the sense, we couldn't estimate them in any way. And those correspond to the exchange contribution, which is of much lower order. Here in this case, we see similar correlation or exchange contributions when we see the results on correlation energy. They're much more relevant. Here they're not very relevant. They are much smaller, even smaller than the error bounds that we can get, but they exist, they are there. And now to control this, we do what we call the bootstrap. And to do bootstrap, we observe a few things. First, we know that NQ is always less than 1. EQ is always less than half. EQ, as I said, is just the relative, or it's the excitation energy. It's the smallest it can be. Oh, it's a bit wrong. There's a typo. It should be greater than equal to and not less than equal to. Because we have a lattice, and the smallest that we can go is half. And then we also proved the leading order, the formula that we derived is of this order. So then we do a bootstrap step. We take a supremum over this expression. Taking the supremum over this expression gives us the bootstrap quantity, supremum over our leading order, and then the error. And by just doing one step, taking all the bootstrap quantities to one side, we achieve such an error bound, and we can achieve this error bound in just one step of bootstrap. And then we have our final result. So that's all. Yeah. So it's the correction that we see from the standard step function, or it's the function that describes this change in the density from the archetype. Yeah, I know, but there wasn't much space in this one slide, so I presented it later. But we do write it before. We do have the definition of NQB before. So we get the right. The scaling of NQB is yes. That's the optimal. Yeah. Actually, we don't need any. It's very simple. There is one thing that is interesting is that just by a mathematical triviality, you can improve your error bounds, and you can get all the way up to kf to -2 plus a very small constant. So it's a full order better than the yeah.
Okay, so the last speaker for today is Oskar Olander.
Yes. Thanks for everyone speaking for the last talk. It's been a long day, but I hope that we can get something exciting out of this talk. I will talk about exchangeability. I think it's a really interesting topic. It's relevant in both probability theory, but also quantum mechanics, and you can go back and forth. Yeah, I work on quantum spin systems, so that's where I will start off. How do you? Oh, great. Okay. Okay. Okay, good. So first, I'll just explain what exchangeability means in terms of for quantum mechanics. You can imagine that you have a quantum system that is divided into subsystems, and you want these subsystems to be symmetric with respect to each other, so you can change their place, but also you need to be able to extend your system to infinitely many such subsystems. So in terms of density matrix, you should be able to extend the density matrix to arbitrarily size and then take partial trace of the copies of auxiliary systems that you sort of added on. And you can put it in the classical setting of a probability distribution. Then you have a finite probability distribution that is symmetric, so you can change the variables. But then you should find a extended version of this where you can take the marginal distribution and get back to where you started, basically. And one key thing when you have this exchangeability is that you can use the quantum definite theorem, and that basically allows you to treat this system as independent subsystems, or at least a mixture of these. That's really powerful. There's different versions of the quantum definite theorem. So you don't necessarily need to have just one simple permutation invariant symmetry. You can also have, for instance, Sn times Sn symmetry, and there you also have a quantum definite theorem. And this is sort of the main tool for basically all of my work that I've done as a PhD student, and I think it's really interesting. I want to show one model where I've applied this, and I call it the n-party model. So here you can see the quantum spins, and they're basically vertices of a complete n-party graph. So you have a graph, and an n-party graph, and you have spins partitioned into these parts, and they all interact with each other, but not within themselves in the parts. And I also allow the different parts to have different sizes. So I call these sizes A1, A2, up to AN, etc. So for instance, if A1 is larger, then it has more spins. But in the end, I will look at the thermodynamic limit, and then all of these will be infinite, but they will still have the relative sizes. Yeah, and so there's an antiferromagnetic interaction on each edge, so they want to anti-align preferably the spin. Then I deduce the theorem that there occurs a phase transition when the spin starts getting magnetized instead of just pointing in random directions, and that occurs with a critical beta that is given by this equation. And I found this equation really cool. So you can view this as a polynomial if you want to. You can multiply up all the betas, so you get a polynomial, and then you get an n-degree polynomial. And yeah, it's really cool. Of course, for an n-degree polynomial, you can have up to n solutions, but there is only one solution that is relevant for the phase transition. Yes, so this is an example of a model which I've looked at, and but I thought about So in this case, it's kind of obvious that it's exchangeable, because you can just add on more spins in each of these parts of the partition, and so it's exchangeable by a priori. But let's say that you're given a system by someone else and you don't know that it's exchangeable. Then it's a natural question to ask, how do I check if it's exchangeable or not? So that's something that I thought about a lot. You can put this in the classical setting if you want. So if you have a probability distribution which is symmetric, so you can exchange the variables in the probability distribution. How do I know if it's exchangeable? So that I can extend it to a larger symmetric distribution. And I asked this question to a guy that knows a lot of probability. His name is Jeffrey Stipe. He works at my university, and he said that you can solve this problem for small cases, but for large cases, very complicated. At least to put it in an explicit form. But I want to show the small case where you can actually solve it. So here we consider a binary sequence, so just a sequence of ones and zeros. And I assume that we just look at the first two digits of this sequence and assume that it's symmetric. So the probability of getting 0, 1 is the same as 1, 0. And for convenience, I denote all of these probabilities by lambda. Lambda 0 means that there is 0 ones in the first two digits, and lambda 1 is that it's exactly 1 1 in the first two digits, and lambda 2 is that there is exactly 2 ones in the first two digits. And then I've assumed that the distribution is symmetric, so we only need 3 numbers to parameterize this probability distribution. And if I like, I can put this in a triangle where this is the space of all symmetric distribution. Where the top of the triangle means that all probability is centered along centered at lambda 1. And the other two corners are for the other two cases. And then you can have, of course, some kind of mixture of everything. So this is the symmetric distributions. But now let's see which part of this triangle is also exchangeable. And one way to do this is by going step by step to a larger number of variables. So first you can go to 3 variables. So you have you look at the 3 first trials of the sequence, and you take the marginal distribution, and then you get this light blue region, which is a little bit smaller than the original triangle, but still quite big. And then you can continue to 4 variables, so the 4 first trials, and then you take the marginal down to 2 variables, and then you get this other shape. And if you continue with this process, you will see that it's going to be in polygon, and it's going to get shrink and shrink until you reach a limit, which is this smooth yellow curve. And that's basically the definitive theorem, that where in the limit you will get this nice smooth curve, and that below this curve you have exchangeability, and above you don't. And for this simple case, you can express this curve quite easily. It's going to be a parabola, and the condition to be below this curve is equivalent to having positive correlation. So this means that if you get a 1 in the first trial, then that cannot decrease your probability of getting a 1 in the second trial. So it's a really nice formulation, but unfortunately there's no simple solutions for the higher dimensional cases. But still, I tried to find some kind of condition that is not exact, but just necessary. So necessary, but not sufficient for higher n. So if you have a sequence of n zeros and ones, I found that the probability distribution to be exchangeable should probably satisfy this condition. I haven't proved it rigorously yet. I've just used some heuristics, but basically it limits the amount of weight that you have on the anti-correlated probability. So you can always have all weight at lambda 0. That just means that you will only get zeros in your sequence, but you can also have just ones. But the thing you cannot have is this 0, 1, 0, 1, 0, 1, 0, 1 alternating sequence. That's not possible. So basically, this gives a bound on how much anti-correlation you can have. So in the the smaller case, you can get a very precise condition. You can say that it has to be precisely positively correlated. But for higher dimensional cases, it's very hard to describe the domain just from a curve and take the convex hull from that curve. It's very hard. You get some kind of complex system of equations that is hard to solve. But if you could describe this kind of domain in an explicit form, you would understand how exchangeability would look in different cases, and you could find which quantum models are exchangeable and not. And that's something I would like to do. Yeah, maybe I should. Yeah, I mean, it went quite quick, but do people know? Do you know why you can go between quantum and classical exchangeability? Yeah, it doesn't doesn't look that way. So that's quite a cool thing, which is quantum tomography, where you can map a density matrix into probabilities. That means that if you understand the classical case completely for all n's and all different sequences, then you understand the quantum exchangeability as well. But there's one detail is that if you go from if you have a spin 1/2 quantum model, that's a 2x2 matrix, that will give you 4 real numbers. So instead of having a binary sequence, you will actually get a sequence that could have 4 values. So it will become messier, but still you can just look at the classical picture and get a lot of understanding. Yeah, I have nothing more to say.